Hello, everyone. Good morning. Thank you for being here. We're the navigation and interaction team working on the SimBot project. Before we get started, here's a brief overview about embodied AI. So this last decade has seen great advances in deep learning, mainly made available due to large-scale compute and data sets. And this has resulted in considerable progress in the fields of CV and NLP. We've also seen a paradigm shift in research towards the amalgamation of these two fields, with growing interest in building agents that learn through interaction as well as exploration of the environment. We've also seen great research in academia as well as industry with the Tesla bot and Alexa SimBot, which basically validates the migration of the community towards embodied AI. So a typical embodied AI agent perceives the environment through vision, speech, and audio, along with grounded language. These inputs together allow for decision-making and carrying out a sequence of actions. So in our very short exposure to embodied AI, we've basically worked with two major data sets which are relevant to our task. One of them is Alfred, which provides us egocentric vision as well as natural language user inputs to complete tasks. On observing some failure cases, researchers noticed that most of these could be resolved through ambiguity resolution as well as clarification, and that paved the way for the Teach dataset, which Amazon released earlier this year. So the Alexa Prize SimBot Challenge basically focuses on advancing development of next generation of virtual assistants that help humans in completing real-world tasks through continuous learning towards common sense reasoning. A typical SimBot is expected to do the following: understand and parse natural language instructions from users, use this to navigate to and interact with rooms as well as objects in the environment, finally clarify, resolve ambiguity, and reason towards a correct action sequence. We'll talk more about evaluation metrics and scores later in the presentation. So basically, we have a set of 9 missions, 5 of which are available to us right now, and 4 which would be available during the general availability phase. Each mission is dynamically created with different layouts as well as object placements to prevent hard coding. Also, we have an unseen set of held out missions, which would form the final layer of evaluation. Also, we have multiple stages in that competition. The first of which is the bootcamp, where teams were introduced to the competition. This was followed by a development phase where teams worked on developing initial stages of the bot. This was followed by a skill certification phase, as well as an internal beta testing phase, which we just got out of. During this phase, our bot is scored by Amazon internal testers around the country. We're now entering the general availability GA phase, where our bot would be available to a larger set of Alexa users with live leaderboard tracking the top teams. A couple things changed over the last year that we have been working on SimBot. So our first spring semester was focused on applying Film, which is a modular solution, to the Teach dataset to try and meet the early submission deadline. We did make the deadline, and we were part of the top 10 teams that moved on to the next stage. However, in summer 2022, Amazon made considerable changes to the entire landscape of the challenge. This included changing the challenge structure as well as the interaction format. We also had a different simulator coming in, moving away from AI to Thor to Arena, which meant a lot of our efforts, which we put in during spring, were moot. Also, the Teach dataset was eliminated, and they came up with their own dataset. This meant that we had to completely redesign our solution going into fall, and that is what we did. And since then, we have iteratively been implementing further versions of our bot.
So right now I'm going to introduce the SimBot challenge description. So the SimBot runs a gamified application on the Alexa Echo device, and the user can interact with the bot through the voice command. And there are 4 main components. The first one is SimBot skill. The SimBot skill is responsible for receiving users' input and parsing the speech input into text. It also invokes the Arena application. So the Arena application orchestrates the whole game playing flow. And then comes the Arena simulation engine. It is a Unity-based engine where the robot navigates and completes the task. It renders multiple indoor scene layouts and the 3D assets. And finally is the action inference service, where we run all the ML models, and everything from dialogue passing to task planning is handled by this action inference service. So the main workflow is that user provide instructions to the bot. It is translated into text by the Alexa speech recognition system that's inside the SimBot skill. And the SimBot skill then sends the raw text to the Arena application. And the Arena application pulls the raw text as well as the images of what the bot is currently seeing. And then it sends all the raw text and visual images into the action inference service, where the action inference service will figure out what's the action sequence to execute and send the action sequence back to the Arena application. So the Arena application sends the action sequence to the simulation to be executed on them. And the simulation engine will respond with a fresh set of images and the execution status for each of the action sets. So the whole process ends with the dialogue, the agent sent back dialogue action, indicating either success, prompt, or error or clarification question. So Arena Simulator supports different actions. So there are two kinds of actions, robot actions and dialogue actions. Dialogue action is used when we want to send dialogue response to the users, and robot actions consists of navigation action and interaction actions. Specifically, navigation actions can be further divided into primitive actions and go-to actions. So one thing to notice is that for the go-to object action and for all the interactive actions that we need to interact with objects, we need to provide the object mask. And for the rest of the actions, we just need to provide, for example, the room name or the viewpoint name or the direction for all the primitive actions. So now I'm going to introduce the SimBot dataset. So there are three parts of the dataset: the vision data, the dialogue trajectory data, and the CDF data. The vision data contains annotations for both the RGB image and the associated ground truth image. Each image has an associated object ID and the bounding box annotation for the ground truth boxes for the various objects in this image. We also have an associated object type with each object. And the action trajectory data consists of human annotated instructions, as well as template generated synthetic instructions. So each instruction consists of the instruction text, the action indices, the question answer pairs between the user and the bot when the bot needs further clarifications. It also contains the CDF data. So the CDF data includes a task description based on the instruction provided by the user, the overall mission goal, the game ID. It also contains the scene information and the additional information provided to the user by the sticky notes. So the sticky notes are used to explain to the users the individual steps needed to achieve the goal.
Let us now look at the demo for one of the missions that we have.
Alexa, go to the freezer in the break room and open it.
So some of the animations have been sped up in the interest of time.
All right, done.
Take the cake to the robotics lab and place it on the red shelf.
Great. What's next?
Turn on the red computer.
If you have used the laser or freeze ray, you can go to the shelf to pick up the object.
Go to the red shelf to pick up the cake.
All done.
Go to the break room and place the cake on the table.
You have completed the task.
Now that we have seen the demo, let us now dive into the system architecture and the different components that helped us achieve this.
So firstly, we have the Arena application, which is the main simulator with which both the dialogue and the navigation modules interact with. And the Arena application has been provided by the folks at Amazon. The language parser takes as input a single natural language instruction from the user and converts it into more sequential granular instructions that are supported by the navigation module. And the language parser has been developed by the dialogue team of SimBot, who will be presenting this Thursday. And diving into the different navigation modules, firstly, we have the scene understanding module, which helps provide the mask for an object in a given image. And we need this mask, as mentioned by Jessica, for interacting and navigating towards an object. And then we have the environment mapper, which stores the location of the different objects as we interact, as we go through the environment and explore it, so that we need not have to search for an object every time we need to interact with it. And then as we keep communicating with the simulator, there are different types of responses that are required to be sent, and this responsibility is handled by the response generator. And we have the state management, which helps multiple users play the game simultaneously without any continuity issues. And at the heart of all these navigation modules is the action processor, which interacts with all these components and coordinates the different actions to ensure that the user's instruction has been executed successfully. So I'll now dive into the working of this action processor with the help of an example. As you saw in the demo, once the user had opened the freezer, the instruction issued was to place the cake on the red shelf in the robotics lab. And after this instruction is passed by the language parser, the sequence of instructions that we have are to pick up the cake, go to the robotics lab, go to the red shelf, and place the cake on the red shelf. And these instructions are now stored in an action queue so that they can be executed one by one sequentially to successfully complete the user's instruction. And at the top of this queue is the first instruction, which is to pick up the cake. And this is currently what the bot sees. And by interacting with the scene understanding module, it is able to get the mask for the cake. And by with the help of the response generator, it is able to request send a response where it is requesting the pickup action with the corresponding object mask. And once this is executed successfully, we have the next instruction in the action queue, which is to go to the robotics lab. And as Jessica mentioned, we just need the room name for this, and this request can also be executed successfully. And once the bot is in the robotics lab, this is the image that it sees. So the next instruction that we have in our queue is to go to the red shelf, and we can see that the red shelf is not visible in this particular view that the bot has. So at this point, what the bot does is it does a look around and gets a 360-degree view of the room and tries to see if it can find the red shelf. And again, once it does this, it is not able to find the red shelf that easily. So this is where the path planning logic comes into the picture. So in across all the layouts that and all the rooms that have been provided by Amazon, there exist 8 viewpoints in each room, such that each viewpoint provides like a visibility to a different portion of the room. So the bot visits these 8 viewpoints sequentially, and at each of these viewpoints, it does a look around and tries to scan for the object that it is looking for until it finds it. So coming back to our example, from one of the viewpoints, the bot is able to find the red shelf in this third image if you look closely. And again, by interacting with the scene understanding module, it gets the mask for it and issues a go-to command to it. And once this is executed, the next instruction that we have is to place the cake on the red shelf. And it again gets the mask for it and is able to successfully execute the place the cake on the red shelf command. And as you can see, our action queue is now empty, and we have successfully executed all the instructions issued by the user. And we send back an acknowledgement regarding the same, that all the actions have been executed successfully. I will now hand it off to Malika, who will go into the details of the scene understanding component.
So the scene understanding component of SimBot is responsible for both identifying what objects the bot can see in its vicinity, as well as for recognizing properties like color, shape, and size of these objects. This module has both an instance segmentation component as well as an object attribute identification component. So in order to interact with objects that the bot can see, the APIs that we use to communicate with the Arena simulator require a mask that can correctly localize the objects of interest. So the instance segmentation module is responsible for correctly identifying and localizing these objects. Given an image of the scene, this model will associate a class with every pixel from a closed set of objects that the bot can interact with. A requirement of this model is its ability to handle identifying objects of varying sizes, varying angles of view, occlusions as well as varying lighting conditions. And we use a mask RCNN instant segmentation model to satisfy these requirements. This model accepts either one image or a set of 4 images from a 360 view that the bot can see, as well as an object category that the bot is currently looking for. And the mask RCNN model is then run on each of these images, and it outputs a set of class predictions, class confidence scores, and their corresponding masks. These masks are further filtered to retain only high confidence predictions using a tunable class confidence threshold. For all predictions that meet this threshold, the masks undergo further post-processing to only include those pixels that satisfy another tunable pixel probability threshold. And this threshold is indicative of the confidence with which the network believes that a specific pixel belongs to the mask of the object that we are looking for. So our mask RCNN image segmentation model is pre-trained on the COCO dataset by mapping classes in the COCO dataset to classes in the SimBot dataset. But not all classes in the SimBot dataset exist in the COCO dataset or even in the real world. There are some unusual objects like time machines, color changers, and freeze rays that exist on the ARENA environment but don't exist in the real world. And so to allow our model to correctly identify these objects, we further train the instant segmentation model on the SimBot dataset. We also ran into situations where our model could not correctly identify smaller objects. So we also went through a round of pre-training to identify small object categories like apples and cans. There are also situations where users might give the bot instructions to interact with objects that satisfy a specific property, for example, to go to a red shelf. And in such situations, the bot needs to be able to recognize object properties like color, shape, and size, and also distinguish between multiple instances of an object using these properties. So the object attribute identification module is responsible for filtering masks that are generated by the mask RCNN instant segmentation model to only include those masks that satisfy a specific condition. So for now, we have only implemented color identification since the missions that we are being tested on only require this capability. Our color identification module uses a set of carefully tuned color thresholds to match masks and filter them out. Vineet will now discuss the remaining components of the SimBot navigation and interaction pipeline.
Hi, everyone. First, we'll talk about the environment mapping module. We use the environment mapping module to track different objects that are present in the environment and especially to locate the objects whenever the path planning module is called. The first part of the environment mapping is static mapping. There are several objects, large and receptacle objects that are present in the environment that are always bound to be present in the same room across different layouts and different rooms. So for example, the fridge in all the missions is bound to be present only in the break room. So to make the localization of these objects easier, we create a static mapping between the object and the room that it's present in. As we mentioned, static mapping can only be used for large objects, but it can't be used for objects that are spawned in different layouts and different rooms. So to tackle this problem, we use a dynamic mapping solution where we associate each viewpoint that we have already visited to the objects that are visible or reachable from that viewpoint. And the next time when we need to interact with the object, we directly go to the closest viewpoint. Next, we talk about the response generator module. The bot throughout the mission must communicate with the ARENA application and also the user to complete the tasks. The components of the response generator are responsible for sending the request to the ARENA simulator and also dialogues to the user. First, we talk about the clarification generator. As Malaika was mentioning, the instant segmentation model for a single object class can provide multiple masks as an output. Thus, in this particular scenario, we might need clarification to help identify the appropriate object. The clarification model is used in the scenario where we cannot disambiguate which mask we need to select. Currently, we only support color to disambiguate the objects. As you can see, the object attribute identifier receives these multiple masks and identifies the number of unique primary colors that we can see in these masks. And then if required, it triggers the clarification question to the user, and based on his output, we identify the correct object. Now we show a quick demo of the clarification generator.
Go to the computer.
Is the color of the computer you are looking for red or blue?
Red. Alexa.
The next module that we talk about is the prompt generator. There are multiple devices in the ARENA environment like the freeze ray, color changer, and time machine, which users are not familiar about how to interact with them. The prompt generator module is responsible to provide intelligent responses to help identify the object and also interact with the object. We show a quick demo again of when the prompt generator is.
Alexa, go to the blue computer.
You can tell me to switch on the computer to use it.
Alexa,
Here we show multiple different types of prompts that we generate based on the object, the action type, and also whether there's an object in hand currently. Next, we talk about the error handler model. The Arena application provides different types of errors to the bot. The error handler model is responsible to process these errors and send back intelligent responses to the user to help them understand the issue and what they can do to fix the issue and complete the mission. Again, there's a demo.
Alexa, pick up the bowl.
Sorry, I cannot pick up another object. Try putting down the cereal box first.
Alexa,
These are more responses that the error handler model provides based on the different error types. The final module in the response generator is the request generator. Every action that needs to be completed by the bot needs to be sent to the Arena application in a structured format. The request generator's task is to construct the corresponding JSON specifying the actions. The module gets a list of primitive instructions and identifies them as go-to, interaction, or navigation action. And then based on the action type that it identifies, it fills the corresponding templates and sends it to the Arena simulator. The final module in the system architecture is the state management. During the challenge, our bot will be and is already tested by multiple people at the same time. So the inference service should be scalable to support requests from different users simultaneously. So to tackle this, we use AWS DynamoDB to store the state information. Each game session is associated with a session ID that is used as a key to store the state information in AWS DynamoDB. And we store and set the state in DynamoDB to get the information. Also, we have an intelligent mechanism to store the object in hand that is used across multiple utterances.
So now we look at the test design. So in terms of the evaluation metric, the most important one is the CSAT or the CX score. Now, this is the rating that is provided by the customers based on their gameplay experience and their whole interaction with the bot. Now, this is the primary metric that is used by Amazon for evaluating the efficacy of our bot. The next important metric is pathline weighted game score. So this is the score that is assigned based on the number of successfully completed subtasks and the time taken to complete each of those subtasks. So if the time taken is more, then the score is lesser. Moving to instance segmentation. So we use mask RCNN for performing instance segmentation. The table shows the result on the validation set provided by Amazon for the mask RCNN model. And we can see that mask RCNN performs particularly well for the small and the medium-sized objects. So in addition to our testing, our bot is also being extensively tested by the Alexa AI team, as well as Amazon's own internal beta testers. So each of these users, they assign a CX score to the bot based from 1 to 5, depending on their overall experience playing the games and interacting with the bot. So as shown by the leaderboard, we are currently at the first position. We have the highest score among all teams participating in the competition. So the graph on the right, it shows how the number of weekly interactions and conversations with the bot has increased over the month of November. The left graph, it shows the relative CX score of our bot, that is Scotty bot, with respect to the best performing team in the competition at different points of time. So we see that our CX score has improved gradually, and we are the best performing team with the highest score for the last 4 days of evaluation. So the graph on the right, it shows the it shows how the duration of the conversations has gradually decreased as our performance and our CX score has improved, showing that the users are now finding it easier to interact with our bot, and the time taken to complete the game missions is also reduced considerably. Now, this slide shows some of the sample positive and the improvement feedback that we received from the users, which we incorporated to improve our bot. Now looking at the non-functional requirements. So the most important one is usability. So since our bot is being used by people who are new to the Arena environment and to the game missions as a whole, they need to be educated in order to understand the entire set of capabilities of the bot and the set of action space that the Arena environment supports. And this is why we use prompts for doing that. The next important one is profanity. So the users can actually throw any sort of instructions at the bot, and it's the duty of the bot to be able to identify profane or inappropriate language, and then flag it and tell the user that, okay, I'm not able to understand these instructions, or I cannot execute the actions that you request me to do. The third important one is interoperability, meaning that the dialogue modules need to be able to communicate with the nav and the interaction modules. And this is done through appropriately designed interfaces between the two components. Now looking at the resource requirements, so this includes the data, which is provided by Amazon, the hardware comprising of EC2 instances, and the non-development human effort. Amazon provides us with two different environments, the ML toolbox for performing testing, and the inference service, which is the main deployment environment. Now moving to risks and challenges. So I'll only be going over them briefly. For details, please refer to our spring presentation. So I'll be talking about the two most important ones, which are product risks and regulatory risks. So one of the most significant product risks is the lack of generalizability of the game environment to the real world. So in the real world, incorrect predictions and actions, they can lead to safety hazards for humans and the public in general, and can cause damage to the bot itself. In terms of regulatory risks, there can be privacy issues due to improper handling of the data, or hacking of the system for malicious purposes. Or if we see that in the real world there are constant public issues due to the agents, then we might see future restrictions on these.
Here's a quick recap of the two major components of our solution that we presented till now. The first one is the research component that Malaika talked about, which is primarily to train and fine-tune an instance segmentation model, also fine-tune thresholds for suitable detection of really small and medium-sized objects, and further come up with a smart solution for attribute identification as well. We also have a multitude of software development components, including the multi-queue paradigm for path planning and action execution, session handling, clarification, error handling, and the rest that we saw. Reflecting back on the last year, we've had a very, very real exposure to a large-scale project, also working with industry. We've had multiple internal as well as external challenges. And I guess we were prepared to attack these or withstand these through highly modular as well as robust code base. We've had really, really strong communication channels, both internal to the team as well as with the dialogue team, also with Amazon. Again, we can proudly declare that we met all of Amazon's deadlines, even though they were ever changing, and ended the capstone on top of the leaderboard.
So there is a lot of improvement for our current version of SimBot. One of the key challenges that our SimBot faces is the inability to identify any other property apart from color. For example, if you look at the first image on the top left, if the user gives the bot an instruction to pick up the cartridge with a hammer on it, our current implementation of SimBot cannot handle it. And so our proposed solution here is to use reclip to ground referring expressions in an image. Reclip repurposes clip and adds an additional spatial relation resolution model to ground all kinds of referring expressions in an image. And so we can use the bounding boxes identified by reclip in conjunction with masks that are generated by our instance segmentation model to correctly identify and disambiguate among multiple instances of the same object. Amazon has also provided a lot of new information that we can use to build a more robust bot. The first of these is the coordinates of the bot as it moves through the environment. And we can use this to construct better maps as well as track which objects our bot has already visited. Soon we will also have access to depth images, and we can use this to generate clarifications based on relations like closer or farther away, in front of and behind, and so on. We also have available to us a highlight functionality that we can use to highlight objects in the frame that the bot sees. And this is useful to draw attention to certain objects and use it to confirm whether a specific instance of an object is the one that the user intended to interact with. Finally, there are several hazards in the Arena environment that can kill the bot, like electrified puddles and things like that. We currently have not implemented a way to track these hazards and avoid them, and we have left this as future work. And so in conclusion of our several months of working on this Alexa Prize challenge, we have developed a SimBot with strong skills in scene understanding, grounding language instructions in an image, identifying when we need more information to complete a task, and how to intelligently use this information to ask questions and create an enjoyable interactive game experience on the Amazon Arena platform. Our team recently went through a rigorous beta testing phase at Amazon, and we are really happy to be closing out our Capstone project at the top of the leaderboard. We'd like to take a second to thank Professor Jonathan and everyone who was involved in the project over the last couple of months. We've all had a really fantastic Capstone experience because of it. So this is the end of our presentation, and we'd love to take questions.
So you guys did a great job, and it's awesome that you got good research results after all of the refactoring you have to do because of all the changes that they made. And if you had enough time to do experiments and not just engineering. And you know from my previous conversations with you that was like my biggest concern about any NCBSD getting involved with Alexa anything. We've done that a couple of times in the past. And during this meeting, there was always lots of explaining why the research didn't get done and why we did all this. So I do have a few questions. I don't want to take too much time because I want to be time for the second half of the team. You did a great job with the presentation. I think you could have given a little more detail on the underlying control. So you did a beautiful job talking about how everything was factored into modules. But like some of the arrows on the diagram didn't really tell me about the control structure. Okay, so you had a single-ended arrow going from an outer capability into your main navigation system, when that should really be a double-ended arrow because the navigation system has to be speaking to you. You don't have to go back to it. So. And then towards the end, you talked about this idea of, a multi-cue control structure between perceiving and acting and clarifying. It would have been interesting to hear a little bit more about that. I guess my overall question, which you already kind of addressed, is what are the main simplifying assumptions in the arena environment that would really have to be relaxed or worked on in order to bring this into the real world? You hit on the big one, which is that you handle color. Color is easy because it's easier to perceive even at a distance, whereas things like shape and orientation become harder when an object is further away. We're going to have to do more navigation to identify things like this. But what about the control flow in your system? Do you think this multi-queue approach is perfectly general, or do you think that you're going to have other kinds of clarification or switching back and forth between thinking and navigation in the future?
I think there's definitely a lot of work that will have to be done if you move the bot to a more real world situation. And I think one of the major things that simplified the process for us is that all of the rooms have viewpoints, and those are fixed locations in a room where the bot can directly navigate to. And this is not true in the real world. If a bot
so those are given to you.
Those are given to you, so you can just
have to explore those and discover those.
Right. So there is no component where the bot sort of figures out a path that does not involve these viewpoints. And this is obviously not a situation that we will encounter in the real world where navigation is more free flowing. So this is one of the things we would have to explore. Another major one is that the objects that we are required to interact with come from a small closed set. It's only about like 85 or 86 objects. And so it's much easier for us to tune an instance segmentation model to identify this small class of objects. But in the real world, there is a lot more variation and a lot more, a bigger number of objects that we would have to deal with. So I guess this is another major challenge with the instance segmentation module that can identify objects in the real world. Do you have anything else to add?
Yeah, I think that just pretty much covers it. And also, like the actions that we take are also like quite straightforward. We just give the mask of the go-to object and directly goes to that. So because the simulation is like quite straightforward for us, it does the entire movement of it finds the shortest path and does the entire navigation. But in the actual world, we would have to figure that out using a A-star algorithm or something like that. So,
okay. So when you get the command to, pick up the cake or you switch on the computer, is there already like a mask dictionary that you have? Or are you running an object recognizer to find out what's what?
So there is an instance segmentation module that is
That
doing the
should
looking
work.
around and identifying the mask. But the actual APIs that we use to interact with the object, for example, if you said to pick up the cake, we don't have any logic of our own that causes the bot's arm to move in a certain way to pick up the cake or anything. So it is just an API call to the Arena application that handles that. So all you have to do is provide a mask and it does the rest.
Okay, so I guess what I'm imagining is that in the future, you would want to have like an exploration phase where you would let the bot go and look at everything in the arena. And if there's any objects that it doesn't understand, maybe let it ask you about those, and then maybe also confirm that what it thinks is a cave is really a cave, and ask about hazards and stuff like that. And then after that, we start doing some tasks that we do. Okay. So I think that's another area that could be interesting for future work. I guess one direction would be to just do whatever improves this and continues to win leaderboards and sort of make the sponsor happy that you're working on their AI direction. But if I think about the larger challenge of embodied AI and really exploring how much, in my case, I care about language, I want to basically have a situation where the robot can go and learn a new arena and then have a dialogue with me to clarify its understanding. So I don't have to actually type in a dictionary of masks, related to image or anything like that. The thing is going to like poke me or send me an email or pop up a screen, where I just have to do a few interface actions to give it the knowledge. So it's interesting to think about what that architecture would look like, and whether it's just a straightforward extension that it's not something. So I noticed that the simulation changes the appearance of objects in the environment. So the cake starts smoking after you fire the laser. Yeah. And I guess you don't care because you already know where it is, or that doesn't change the mask enough that you stop recognizing the cake.
Right.
But I guess in the real world, you would have to deal with objects that have polymorphism and can actually change their shape. And there could be sort of in dynamic circumstances, all of a sudden you don't recognize what something is. The part of the grounding is always not just recognizing what an object is from one perspective, but actually being able to recognize it from any viewpoint in the scene. So if you're doing this kind of grounding task, you're riding around in the environment, as soon as the mentor tells you that's a cake, then that's great. Now as I move around, I can use geometry to sort of verify what that thing looks like in the direction. Very cool. So my last question, then we'll get on to the next team. Really like the diagram where you showed your performance versus the best performance, and where you went from like less than 50th percentile to the top. What do you attribute that to? So did you just look at your own modules and make them better? Did you learn anything from the experiences of other teams? Was there any cross communication? Did you adopt some cool ideas from other teams? What happened here?
Yeah, so I think the main thing that helped us is that we got daily feedback from the beta testers.
Mm-hmm.
So Kush showed some sample positive and negative feedback that we got. And so we read through those every morning, and some of the feedback was really useful. So they would say that, we don't know how to interact with a color changer device, or I said go to the computer, but the bot went to the blue one instead of the red one, things like that. So from those feedbacks, we were able to figure out some pain points, like we need to be able to identify color, we need to give the user prompts, we need to generate intelligent responses to errors when the bot can't proceed with completing a task. And I think the two of the main things that really helped are interacting more with the users, and particularly through prompts and the error responses. because there are a lot of objects in the environment that don't exist in the real world. And so it's really hard for a user to know that, okay, to switch on a freeze ray, I need to go find the blue computer, find a red button on the blue computer, and then switch it on. And there are no prompts
Getting
in the
user
environment.
grounded.
Exactly. And so users also have a tutorial that they can take before they play the game, but the tutorial is not very extensive. It just tells you, hey, you can pick up an object, you can go to a certain point, but it doesn't give them any information on how to actually interact with these weirder objects in the environment. And so
So do you think it really was mostly being more supportive of the user and not that you made module X 10 times better?
I think,
I
yeah,
think
go ahead.
it works both ways. So first of all, we're trying to get the user accustomed to our environment and getting them to know how the system works. But I think we also added the clarification module as part of this. We also added the prompt generator as part of this. So these weren't part of the version 1 that we created.
Oh, okay, so you actually changed your.
Yes, so
In response to the
actually
feedback.
add a couple more components as part of the initial version that we had come up with. So the first version, I think, had the action processor, the environment mapper, and parts of the response generator.
Mhm.
And we didn't even have session handling. So one of the things that we saw were like with user testing, we saw that multiple users had some conflicts when there were 2 devices logged on at the same time. So that brought in the state management module. We also have the prompt generator as well as the application generator that came in later.
So you guys are in a position where you could definitely tell a story about how you had to be very agile and then constantly impact your design. And rather than just focusing on the thing that was sort of imposed by Amazon over the summer, you could basically say, wow, we had to be really nimble because every time we heard from the user, we realized something, you know, that we needed to our system. So do you think that's why you guys are at the top of the leaderboard? Because you basically made the most out of the user interaction?
I definitely think that is the primary reason. We had.
Is there going to be some kind of a workshop where you get to share technical details with the other teams?
Not that I know.
I don't know.
Okay.
We've entered GA, so the real question is what the real customers look like.
Okay. And what the real testing environment is like. Yeah. Yonatan, anything else you want to add or any other questions you want to ask?
No, I'll maybe say that in response to the early question you had about sort of building maps and navigating from that was all on the original timeline and was initially being implemented when Teach was the benchmark last semester. And then Amazon's focus was more on dialogue. And so therefore that fell away. But I think that the commonality in addition to what was brought up about the top 2 teams is that we're basically 2 teams that actually had a team. So I think that a lot of people walked in and said, oh, it's a dialogue path, so I'll focus on dialogue. And it's true, we need to adapt this, but if you don't have a good model of the world, so you can efficiently find objects and other things like this, then you're just doing what you're using. So I think that people basically downweighted that in favor of dialogue, and that didn't happen here. And so instead of actual representation and mission service.
All right, thanks, guys. Good job.